Hello guys, I'm delighted to present this multi-part series on NARDL Bounds Testing approach to cointegration. This estimation model was developed in 2014, as I note here, by Shane Yu and Greenwood Nemo, following the wonderful work on ARDL cointegration approach a little over 10 years earlier by Pesaran, Shin, and Smith. Now, similar to the ARDL model, this unrestricted error correction model, if I may put it that way, can entertain a mix of I0 and I1 regressors, all right, but no more than I1 though. It can also be viewed as an unrestricted error correction model, as I already mentioned, since the long-run terms, as you see right here, are clearly specified. However, unlike the ARDL model, this model here includes a decomposition of the regressor into its positive and negative changes right there, right? As a result, the model can best be described as an asymmetric error correction model. Now, in this series, I'm going to show an example of the NARDL estimation process using eViews, as well as provide interpretation of the output, which I'm sure you are going to be looking forward to. In this introductory presentation, though, I'm going to describe the motivation for this modeling approach, beginning with a description of the concept of asymmetry, the reason for which this cointegration approach is considered nonlinear. So I'd like to begin with something a little cheesy, hopefully entertaining. All right, so using a usual approach, the news of a negative change, something bad in the character of an otherwise good kid, would naturally provoke a harsh reaction from the parents, right? However, the child's good behavior, which though would absolutely delight the father, would not, however, come as a surprise, since good behavior is more consistent with the child's character. And so, as you can see, these two sides of a change in the child's behavior do not provoke a uniform impact on the parent. In econometric speak, we'd say the dad's reaction to the child's positive and negative changes is asymmetric, in that they are not equal in magnitude. And so let's bring this home. All right, let's consider two variables: market volatility, which is a risk indicator, and oil price. All right, now suppose we have a positive relationship between these two, meaning that when volatility goes up, oil price tends to go up, and when volatility comes down, oil price tends to come down. The question though is the magnitude of price change the same in both directions? Symmetric relationship means the degree of impact of x on y is going to be the same when x goes up, x positive, and when x decreases, x negative. Now though, but might it be that an increase in volatility has a stronger impact on price than a decrease in volatility, perhaps vice versa? If we find that the magnitude of impact is not the same on both sides of the change, then we're going to conclude that the impact of volatility on price is asymmetric. Now, let's dig deeper and consider this two variable regression model. The most important parameter here is beta 1, all right, B1. This parameter helps us draw conclusions on three important aspects of the relationship. First of all, it's going to tell us if a relationship exists to start with. All right, so if we test hypothesis on B1 and it is statistically significant, then we're going to say, voila, we do have a relationship between y and x. Secondly, the sign that B1 has is going to give us a sense as to the direction of relationship. For example, if B1 is negative, it tells us that when x goes up, y goes down. When x goes down, y goes up. Thirdly, the value of B1 is going to tell us of the magnitude of impact on y as a result of changes in x. And so, for example, let's say that B1 turns out to be positive and has the value of 2. What that tells us is that if x increases, y is going to go up twice as much, and if x decreases, y is going to decrease twice as much. That's symmetric movements. However, this assumption of symmetry may not hold up in reality, and this is what provokes research in this field of asymmetry. So now what the nonlinear autoregressive distributed lag model does is to separate the reactions of y to negative and positive changes in x, so that this x right here, to capture the effects of asymmetry, would be decomposed into partial sum of positive change in it, which we're going to call x positive, and then partial sum of negative change in x, which we're going to call x negative. So both of these are going to be separately included in the regression model. And we're going to have something of this form that you see right here, which comes out effectively to be a three-variable model: y, the dependent variable, x positive, and x negative. So now, as we move into NARDL, a flashback to what we learned in the ARDL series. Again, there are two components to this: the short run component and the long run component. And here, this is a symmetric model because, as you can see, x is not decomposed, and this is what we're going to be focusing much of our attention on. In the NARDL representation, as I showed at the outset, you see that decomposition right here. So each of these coefficients, phi positive and phi negative, would be included in the long run test of hypothesis. So now, in that sense, x is going to be decomposed, as I mentioned earlier, into its positive and negative partial sums in this style right here. For increases in x, it's going to be the greater of the change in x, or 0. And for decreases, it's going to be equal to the lower of the change in x, or 0. So I present this intuitive illustration, if you like, where out of this original series, right, let's say that x changes in value from 5 to 1. So this is, of course, a negative change of -4. And in this case, therefore, x positive is going to have the value of 0, since 0 is greater than -4. So that's why you have 0 here. X negative, on the other hand, is going to have the value of -4, because -4 is the lower of 0 and -4. And so you play it out. And therefore, when you run a regression, so to speak, on x positive and x negative, and let's say the coefficient of x positive is 1.51 and that for x negative is 1.23. So as you can see already, there is a difference in terms of the slopes b1 and b2. The question though is the difference between these two numbers statistically significant? So now, moving directly into the bounds testing approach, we're going to use the bounds test in the sense of Pesaran and test the hypothesis that there is no co-integration. All right, so this is the null hypothesis, which if we reject, we're going to be concluding that the variables are co-integrated. However, in the presence of asymmetry, because of the coefficients that are included in the inquiry. However, for us to make a judgment on asymmetry, we're going to be constructing the asymmetric coefficients shown here, which is going to be the ratio of the coefficient of x positive and the coefficient of the lagged value of y in the long run components of the model, which you see right here, and ditto for x negative, each of which preceded by the negative sign right here. And so we construct this statement of hypothesis and test it. If we reject it, then we have evidence of long-run asymmetry. In other words, the magnitude of the change in y when x increases is not the same as when x decreases. Further, we're going to construct asymmetric dynamic multipliers. What are those? They're going to help us observe how y, the dependent variable, adjusts to its new long-run equilibrium following a negative or a positive shock in x. And so what you see right here is a statement suggesting that we're going to be observing how Y traverses along the ways from the near term to the long run on account of a change in X, a positive change in X in this case, a negative change in X in this case. And that's going to be quite telling because it's going to help us understand that the nature of that adjustment along the ways. So when they developed this model, Shane and his co-authors conducted an empirical study on the relationship between unemployment and output. And they found a strong evidence of long-run asymmetry. They find in particular, as I write out here, that unemployment is more sensitive to economic downturns than to economic booms. In effect, they find that firms are quick to fire but slow to hire, which in the wake of the COVID-19 pandemic in 2020, we saw a good evidence of that because right after the first couple of weeks of the pandemic hitting the United States, we had over 30 million people lost their jobs. Another important evidence in their study is that when the regular ARDL was applied, they actually found no evidence of long-run relationship. But that's because the model was misspecified. They needed to account for asymmetry. Because once that was done, a clear evidence of an asymmetric long-run relationship emerged, which led them to conclude that correctly specifying the nature of a long-run relationship in the context of NARDL in this case is critical if one must avoid drawing incorrect inferences or worse still, making incorrect financial and perhaps even policy decisions.